Hi everyone, Miss Coco here. Welcome to lecture discussion for section 3.6. This is a little bit more in-depth explanations of things that you encountered in your My Math Lab lectures and readings, or book readings, I should say. So 3.6 is analyzing arguments with truth tables. Basically, this section is all about everything that you learned in chapter 3. So this is like the ultimate conclusion of what you have learned. And we're taking these topics that we learned, that we're going to go over here in a second, and we're applying them to logical arguments. And when we learned about logical arguments at the beginning of chapter 1, when we did deductive and inductive reasoning, we learned about premises and conclusions and how to use them by case to come to a conclusion, which is inductive reasoning. And then from general big case to case by case to come to a very specific conclusion, which is deductive reasoning. Now in 3.6, logical arguments follow deductive reasoning to see whether or not the argument is valid. Okay, so that's what we're doing. But before we do this, I want to go over a few things that we have learned so far. We have learned about if then Q statements, right? They're equivalent to the truth table of saying not P or Q. Also, we can negate an if then statement by using the P and Q. This is and, not Q. All right, so these two things are equivalent. So their truth values are equivalent. These truth values, their truth table values are equivalent. We also, remember, we created truth values for if P implies Q is true in all cases, except for whenever the P if then is true and the Q is false. That gives you the lie, which you were lied to, and it's a false statement. That's the only time it's false, is when that is the case. We also learned about conjunctions, which is the upside down V. And this is what the truth table looks like. There's only one case with a conjunction that's true in all cases. And remember, it has to be true in both cases. It has to be that intersection that we talked about of the two circles coming together to be true. And the or, which is just the V, it's a disjunction. Remember, and is a conjunction. So the or is the disjunction. And this is what the truth value looks like. And these, it could be true or false or both. And then the statement will be true. However, there's only one case where you have a complete false, is that's when P and Q are false. It says P or is false or Q is false, so therefore this entire statement is false. Remember De Morgan's law? We also talked about that. When you negate it, you flip the inside. So this was and, it goes to or, and then you negate P and Q. I forgot to negate Q right here. If you have an or, it flips to and then you just negate both P and Q. So those are equivalent. These, when you see equivalent, remember equivalent statements mean that they have the same truth table. So that's everything basically that we went over. We did things like all and some quantifiers, but we'll talk about that at a later time when we do a test review. Okay, so 3.6. We have this big idea about logical arguments, and I really recommend, we didn't go over it, but this would help your reading. This kind of confuses people when we do Euler tables with logical arguments first. So I do want you to read 3.5s, take notes on the big ideas, especially the premises and conclusions and valid argument definitions. Really take those away, and you can just read over the other stuff just to get your toes wet with using Euler diagrams, but you're not going to be required to turn these notes in or even know how to do an Euler statement when seeing whether or not an argument is valid. But I will tell you, this will help you if you read it, and you definitely have to read it to get at least these definitions. All right, because these are big ideas. So let's talk about this a little bit more in depth. A logical argument uses deductive reasoning. So this is the definition. that I'm using for 3.6 uses deductive reasoning and the conjunction and after every premise to see whether or not an argument is valid or invalid. Meaning we're going to do if-then statements and to create truth tables. So we're going to basically take statements such as this statement right here in a premise, and we're going to turn it into P and Q and use the word and to see if the conclusion is valid using your truth table. That's basically what we're doing in a nutshell. So this is an example right here that I just underlined of a logical argument. No accidents happen on purpose. This is a statement, and it's also the first premise. Spilling the beans was an accident. This is a statement, and it's another premise. And it follows, this line means that we're coming to a conclusion, and the conclusion follows this line, and this conclusion states that the beans were not spilled on purpose. This is a statement. It's also the conclusion. Okay, so we're going to learn more about this being a logical statement. If you looked at the Euler on 3.5, which is this is actually taken from, you'll see that this is a valid statement, and it makes more sense whenever you look at that. So check that out. It's once again 3.5, and just give it a look over, get these definitions out of 3.5, and then move on. Note, the big idea here that you really need to take home is we are using deductive reasoning. That means going from a general case, using specific cases or premises. So one big premise starts us off, then another little one, and then we're going to get to a more specific conclusion. All right, so we're going from the big to the small here. Not the case by case, but from the it follows, each step has to follow the next to get to your conclusion. Just like within math, when we are like an example in deductive reasoning with math, maybe you want to solve this mathematical statement here. This would be your first premise, and then you'd have to use the next step, which would be I can subtract 1 from both sides due to the law of, I forget what the law is called right now, due to this law right here that we've learned millions of times, and Ms. Coco has learned millions of times and has taught millions of times, to get to this statement. Then the next premise says I can divide both sides by 3 to balance the equation, and therefore R equals, and because of this, R equals 2/3. So this is starting with the big statement, doing case by case, specific case steps that follow, and R equals 2. One thing you need to realize is that each one of these premises must be true in order for the conclusion to be true and to be called a valid statement. And in a truth table, the end result looks like a tautology, which is it's true in all cases, right? This is the big end result, the very last column that we always get to in truth tables. That's called a tautology, and it looks like this, all right? So that's what we're going for. It's that a tautology means it's the end result is all truth, or all true values, or T's. Okay, so let's look at this a little bit further with actual examples. If you notice, before I used to teach 3.5, and I realized I really didn't need to teach it, so we're not going to teach it. And it says in the previous section on my guided notes that we used Euler diagrams to test the validity of arguments. However, that's not the only way, and it is pronounced Euler, by the way. We can use this if P then Q in truth tables, which these work in all cases, no matter if it's a Euler, Euler works in really simple cases like these one sentence off statements that don't have if and then, but they can even, truth values can work in all cases. So that's why I preferred to teach this. I felt like it might have been a little bit redundant, but it's kind of a cool idea. And also I've noticed that students get a little bit bogged down with the wording with these, so I wanted to make sure that there was no one getting bogged down. All right, so let's go into this a little bit further. Our first objective is that we want to identify using a truth table to determine a validity of an argument. So our goal, this is our objective 1, our goal is to determine if this argument that is followed is valid or invalid. Here is the argument. If there's a problem, then I must fix it. So that's our first premise. We call this P1 for premise 1. The next premise is there is a problem, so this is P2. The line means that I'm coming to a conclusion. So you're going to see this. I'm going to use a line always. And then this is my conclusion. I must fix it. All right. So our first step is to, and this is going to be every single time you're going to do this. When you are seeing validities of arguments, this is the exact steps. Now, the only difference is it's going to be a little bit like tricky, but you're going to basically perform these steps in order with a little bit of thinking through some of the logic ideas, all right, and applying some vocabulary. So first, you figure out the premise 1 and premise 2, and then you let P represent there's a problem in the first premise, which is the if. It comes after the if. And then Q represents the after the then, I must fix it. Your second step is to apply your if-then statements. So what you're basically doing is you're not apply your if-then statements. You're creating symbolic statements. So that's your second step. You're going to create your symbolic statements. So premise 1 says P implies Q. So we're basically getting rid of the words. And premise 2 says, well, this is P. There's a problem, which is just equal to P. And my conclusion is Q, which was I must fix it. The third thing is that now we are going to decide whether this argument is valid. We must determine whether the conjunction of both premises implies the conclusion for all possible combination of truth values for P and Q. So what this means is that we are going to write the conjunction of the premises as the antecedent of a conditional statement and then write the conclusion as the consequent. So what I mean by this is you're basically going to take premise 1 and premise 2, and I'm going to write it out here. It's written out here, but I'm going to do it by hand. Don't worry about this right here. Don't worry about this. I'm going to take premise 1, P, then Q, and I'm going to take the conjunction, which means the intersection or the and, right? And I am going to meld it with my other premise. So this is premise 1, and this is premise 2. Okay? So I'm going to take this. This is my first state. Oops. Didn't mean to do that, huh? So this is my first statement, my first premise, my second. I'm going to box it out. And then I'm going to take the conclusion implies Q. And I'm going to create this conjunction in symbol form. So that's my third step. And they actually call this step in the book, the third step is form the symbolic statement of the entire argument by writing the conjunction of all premises. So basically the reason why you want to find the conjunction and is because in deductive reasoning, remember I said we have to use that and statement because it has to follow. So it has to be true in all cases. And is always the thing that's always the only time it's true is whenever it's true in all cases. So that's why we take the conjunction because we're sticking with deduction. Okay. And for a statement to be valid in deductive reasoning, it has to be true in all cases to follow the next case. So that's why we use the word and. So then our fourth statement is we're going to take this final conjunction and we are going to put it in a truth table, such as this one. I'm going to make this a little prettier. And I know I'm running out of time. This is getting a little bit longer than I want to. So I'm going to take and I'm going to create a truth table for this statement to see what the end result is. So here I have P and Q, which we know the cases are true, 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 false, false, true, and false, false. All right, so let's see what that looks like. Make this a little prettier.